In this video, I will introduce the highly efficient boundary element method for solving linear partial differential equation, support GPU acceleration. I will provide source code in MATLAB so that you can use it in your own research. If you're not numerical expert or PDE expert, but you see some reference apply this method to solve problems like in fluid mechanics that you don't know how to implement, then this video is for you. Before we talk about boundary element method, we first recall some volume discretist method, like finite difference method. For example, we want to solve the electric potential distribution inside the domain between two concentric circles. The inner surface has a potential of phi naught, and the outer surface has a potential of zero. The electric potential is governed by Poisson equation. In FDM, we first discretize the domain using a mesh, then write the PDE as difference equation on the mesh nodes, then apply the boundary conditions on the boundary nodes. Last, we solve the linear system. In the whole process, we focus on solving the potential. Let's get a closer look at the Poisson equation. One applies Laplace operator on the potential, then output the charge density. Since the Laplace operator is a linear operator, we can use the inverse of the Laplace operator. We apply the inverse on both sides of Poisson equation. Then we get an inverse equation. This equation accepts charge density as the input and output potential. This implies that given an electric field, one has two ways to describe it. Either use the charge density or use the potential. Two descriptions are equivalent. This concept is similar to that of quantum mechanics, that given a wave function, you can either use a momentum representation or position representation, and these two relate each other with a linear transformation. For VDM, they seek for potential directly, while BEM solve for the charge distribution. For most problems, charge only distribute on boundary, so only the boundary is meshed, which largely reduces the size of the problem. BEM is very suitable for problems with a given natural boundary condition at infinity, or the geometry is far away from each other, because you do not need to mesh the space between boundaries. For these types of problem, BEM is highly efficient. We will give an example that BEM is at least 2 orders of magnitude faster than VDM for the same accuracy. We want to use a representation of the inverse operator for implementation of boundary element method. This operator uses charge density as the input and produces electric potential. But we have already known this relation as Coulomb's law in high school physics. The potential produced by one point charge is just 1 over 4 pi r, where r is the distance between the charge source and destination. Then you sum up all the inference of charges. To implement BEM, you first place a charge on the surface with a strength vector Qi, sum of the inference to compute phi, and matching the boundary condition on the surface Q equals A times Q, phi equals A times Q. Then solving the linear system. On the right, we give a schematics. The scatters are point charge. You adjust the strength of these charges to match the boundary condition on the surface, which produce a linear system. Another advantage of BEM is they are highly versatile. For each type of linear PDE, you have an inverse operator. In PDE theory, we call this inverse operator as Green's function. They all can be solved by BEM. For example, for 3D Laplace equation, you have a Green's function minus 1 over 4 pi r. This equation can be used to describe electrostatics, diffusion, and heat conduction. For Helmholtz operator, you have the similar form of Green's function, but with extra factor e to the minus 1 kr. This equation is applied to electromagnetics, acoustics, quantum mechanics, electric double layer in solution or plasma. The third one is the Stokes law, which involves two capital PDE, describes the momentum and mass conservation for a low Reynolds number fluid flow. The Green's function has a tensor form, which is more complex than previous example. Basically, it describes how fluid flow responds to a point force. In Stokes flow, we also call this function a Stokes let. Now we will walk through the example of Stokes flow partial sphere in 3D. We first set the parameters of this problem: the radius of the sphere, the constant velocity of the sphere, ux, uy, uz, which has three components: viscosity of the fluid, and at last we create a mesh on the surface of the sphere. We use the sphere function in MATLAB to create the mesh. The second step is to create an array to store the stiffness matrix and the load vector. Remember that we will solve the linear system AF equals B, where B is the boundary condition, that's the velocity at each boundary node. For each element in the matrix Aij, which represents the ice force influence on the J's velocity, this is just the Green's function for Stokes flow, but we will calculate the distance between the I and j nodes and the vector distance, both the vector and the magnitude. But for the element at the diagonal of A, we will calculate the self-interaction, that is the force on the node's influence on its own velocity. Remember that Green's function scale as 1 over r. When r approaches 0, the Green's function blows up, which leading to the singularity. We will regulate the singularity by placing the force underneath the surface. This regulation won't affect the accuracy of our method. Lastly, we will solve the linear system using the backslash operator in MATLAB. We obtain the force distribution on the surface, as shown in the figure on the left. On the right, there are profiling information. It uses about 1.2 seconds to assemble the stiffness matrix and use 0.16 seconds to solve the linear system. The total drag force on the sphere is a well-known result. At 6 pi radius mu times velocity, the total error is about 0.5%, which is fairly accurate. If we compare the method to some VDM, such as the finite element method, which requires very large-scale mesh to achieve high accuracy. This is an example by a Python library, FEM. To achieve an accuracy of 0.4%, it has to use a cylinder domain that is 100 times larger than the sphere. And the total computational time is in the order of 100 seconds. If you have powerful GPU, you can further boost the efficiency of BEM. If we check the profiling information, most of the computational time is consumed on the assembly of the stiffness matrix. But the assignment to each element of the matrix is independent because the Green's function uses the position vector as the input. In GPU programming, we call this embarrassingly parallel task. In CUDA, you can just simply define a kernel and distribute the kernel on threads. Solving the linear system can also performed on GPU. Because A is a dense matrix, generally we use a direct solver to factor A. The core step is Gaussian elimination, the method taught in math course in high school. GPUs are highly optimized for Gaussian elimination. In CUDA, there is a specific library that is used for solving linear systems, known as QSolver. You can simply call this function in MATLAB using backslash operator, as shown in this slide. In summary, BEM is a powerful tool for linear PDE which solves for charge instead of potential. And it is highly flexible. All linear PDE can be solved by BEM. Only boundary is meshed, so it's highly efficient. BEM can be implemented on GPU, which further enhances its efficiency. Overall, you can achieve 3 orders of magnitude speed up compared to VDM for a specific problem. I will leave a link for downloading the source code for this example in the below. I have created a repository for this BEM project in GitHub. But if you have further questions, please email me.